Hello everyone. In this video, we are going to study the rotational energy states of a rigid diatomic molecule. I am Dr. Siva Prakash, Assistant Professor, Physics, SR Madurai, College for Engineering and Technology. Rotational energy. The total energy of the molecule is categorized into the following. E equal to E electronic plus E vibrational plus E rotational plus E translational plus E nucleus spin. Electronic energy. The energy rises due to the transition of electrons between two energy states. The vibrational energy level is due to the molecular vibration. Rotational energy is due to the rotation of a molecule about an axis. Translational energy is the energy due to the linear motion of the molecule, and the nucleus spin energy is due to the energy arises due to nucleus spin. Here we are focused only on rotational energy. It is the kinetic energy of a molecule due to its rotation about its center of mass. The understanding of rotational energy is the key concept in molecular physics and in spectroscopy. So what is linear motion? The ball is actually moving from one point to another point in a rectilinear motion. Rotational motion. You can see the same football is rotating about an axis. So on the other side, you can see a HCl molecule is rotating about an axis. The axis is actually perpendicular to its bond length. So the rotation about an axis perpendicular to its bond length gives rise to a spectrum called microwave spectrum. The picture given in the slide is the microwave spectrum of CO2 molecule at different temperature 150 Kelvin and 500 Kelvin. Rotational energy for a diatomic molecule. Basic concept. Generally, molecules are not rigid in nature. Due to external agencies like force acting on it, it rotates about an axis, gives rise to rotational energy levels. These energy levels depends on the moment of inertia and the rotational quantum number. Let us see the derivation of rotational energy states for a diatomic molecule. So consider mass of M1 is located at some point and M2 is another mass which is located at some other point. So these two masses are actually kept at a distance capital R. So the system is actually rotating about an axis perpendicular to the capital R. C is the center of mass and R1 is the distance between the mass M1 and the center of mass. R2 is the distance between mass M2 and the center of mass. So just consider this system is about to rotate in an anti-clockwise direction. So you can see the molecule is about to rotate about an axis perpendicular to its bond length in an anti-clockwise direction. The kinetic energy of any particle of mass m moving with some linear velocity is given by E equal to 1 by 2 mv square, where m is the mass of that particular particle and v is the linear velocity corresponding to that particular particle. So we consider two body system, particle 1 and particle 2 having mass m1 and m2. So I just derived two different set of kinetic energies E1 and E2, where v1 is the linear velocity of particle 1 and v2 is the linear velocity of particle 2. Motion is actually rotating about an axis. We have to convert the linear velocity into angular velocity. The formulas provided is actually converting the linear velocity into angular velocity. So by using this relationship in equation 2, we can derive a new expression for E1 and E2 like this, where omega is angular velocity of the particle, R1 and R2 are the distances of mass m1 and m2 from the center of mass. So the total kinetic energy of the particle is given by the summation of E1 and E2. So I just summate the two equation and I just take 1 by 2 omega square common in both term, and inside the bracket you have m1 r1 square plus m2 r2 square. I consider this is equation number 4. We know that the moment of inertia is nothing but the product of mass and the square of the distance between the mass and the center of mass. So I just derive I1 and I2. By adding I1 and I2, I come to a conclusion of a new formula I equal to m1 r square plus m2 r2 square. I just use this relation equation number 5 in equation number 4 and finally get an equation E equal to 1 by 2 I into omega square, where I is moment of inertia and omega is the angular velocity. So I just multiply the moment of inertia on numerator and denominator as shown in the slide, and finally I derive an equation which is equal to L square by 2I, where L is the angular momentum of that system. So at atomic level, the rotation leads to the quantization of the angular momentum, with the value is given by L square equal to L into L plus 1 h cross square, where h cross equal to h divided by 2 pi, h is Planck constant. So substituting this value in the previous equation, you will get E equal to L into L plus 1 h cross square divided by 2I. So I just plot an energy level diagram for this rotational energy state. So I just consider energy in y-axis. So if I substitute L value which is equal to 0 corresponding to that equation, results the energy which is equal to 0. If we substitute L equal to 1, which leads to energy h cross square by I, and again I am increasing the L value to 2, and it leads to 3h cross square by I, and it goes on like this, L3 and L4. So look at this energy level diagram. So they are not equally spacing, right? The applications of rotational spectroscopy. So these rotational spectroscopy is actually used to determine the molecular structure, especially the bond length between two atoms. And the same rotational spectroscopy is used to identify the isotope type, and it is used in remote sensing, and also the technique is used in astrophysics to study the molecular clouds. Thank you.